Hello, my name is Matthew Crawford, and I would like to welcome you to the very first episode of the MetaPrep Math Club for Adults. The Math Club for Adults is a meeting, educational meeting for those who are enthusiastic about mathematics, those who want to find different mathematical topics to share their joy of mathematics with their kids, perhaps, or perhaps you're a teacher and you want to share with the classroom, or people who want to improve their problem-solving abilities. What Math Club is not is something for professionals. We are not going to cover the kinds of topics that someone who has gone to graduate school studying mathematics, or anyone doing, actuarial or any kind of real world research. We're not going to cover that level of mathematics. This is going to be largely elementary mathematics, perhaps with a little bit of calculus and beyond once in a while. But we're going to cover a lot of the historical topics of mathematics up and through most mathematics, which is utilitarian for the common professional. Uh, just a note about our first episode. I had just changed the hard drive on my computer, and that resulted in a change of the settings for my microphone driver. As a result, you're going to hear I have kind of a lispy sound due to my breath hitting the microphone, but this will be corrected in the future. And otherwise, hopefully, we'll be able to make this a better and better experience. Maybe we'll add some nice music and whizzy graphics in the future. Anyhow, if you enjoy this first episode, which is on the topic of figurate numbers, you can join us at www.metaprep.net for a future Math Club event. Thank you.
So I'm gonna give kind of an intro here in a second, where I'll actually probably start after we clip the video. But well, welcome to the MetaPrep Math Club. Today we are going to talk about figurate numbers, which has a history that goes back about 2,500 years, maybe further, probably further. With a lot of early mathematics, we really just don't know. We don't know, to some extent what the Egyptians were doing, because they were doing things like measuring areas with dots, and it may be that figurate numbers was part of what they did. Their forms of multiplication kind of looked like figurate numbers. So without further ado, let's talk about what figurate numbers are. And I encourage everybody to do something like open like a basic Wikipedia page. Maybe just type in figurate numbers for the first time. Oops, don't do that. And maybe be able to take a little bit of a look at the history as we go. Yes, there's a certain amount of this that gets attributed to Pythagoras, if I recall correctly, and but I really do think that it goes back further. Like I said, I think the Egyptians were doing some of this prior to that, but we just don't know. But here, this is what figurate numbers are. It's where we create figures with dots, basically, and this can be done for all kinds of reasons. Seeing it might help us sort of see a geometry, where we're counting and doing geometry and perhaps some algebra at the same time. So it allows us to do a lot of things, and it was created before some of our more modern systems of algebra and geometry, and further arithmetic and calculus were. In fact, a lot of the things that we're going to take a look at are very much like the calculus that was developed 2,000 years after Pythagoras. So let's do a basic one. Let's do triangular numbers. And I'll go ahead and say this. A lot of the ones that we're going to study, the figurate numbers that we're going to study, are specifically called polygonal numbers. And I say they're called that. One author may call it one thing, and one author may call it another. But we'll try to stick to the most traditional terms. But the polygonal numbers are like triangles, squares, pentagons, hexagons, and so forth. But here with triangular numbers, we start with one dot, and then we build up higher and higher, creating larger and larger triangles as we go. And you may also see this done at times a little bit differently. Let's see, triangular numbers. Sometimes you see the dots arranged like that, more like an equilateral triangle, where everything looks the same on every side. So 1, 2, 6. And the next one, which is 10. And so, it's just the most basic example. We need 3 sides to make a figure. So it's the most simple one. And then we have square numbers also that form squares. And we can build these up. I'm gonna build one up a little bit differently. Well, first I'll do this. See, there's the first square number, which is just 1, and then 4. And people know how to calculate these better. In fact, we still use the term square when we take a number to the second power. So 3 squared is 9. 3 times 3 is 9. And 4 times 4 would be 16. I'm going to do the next one, though, a little bit differently. I'm going to use multiple colored dots. Just because this was one of the first interesting things that I ever noticed about Figurate numbers. And I actually noticed that, I think, with the numbers first, but we can see it sort of physically with the geometry. Sorry, I'll try to get my pen straight here. But we can notice it physically with the geometry using these dots. And what do we see with these dots? Oops, I went all the way out to 5 times 5. I skipped 4 times 4, didn't I? We might call that the 5th square number verbally. But it would go 1, 4, 9, 16. I skipped to 16, went to 25 in order to, I think I was just adding colors to the stack here. But what do the colors tell us? Anybody have a thought on that? Well, one thing the colors, well, if we number the dots from each color, we have 1 green, 3 blue, 5 red, 7 gray, and 9 black dots. And that forms a pretty easy to tell pattern. Those are the odd numbers. They're increasing by 2 at a time. And we actually have a name for those numbers, where each one added on becomes the next larger square number. I think that's called a nomen. Actually, I'm not sure how to pronounce this, to be honest, because it's something that I only saw in books, but usually the TN is like an N, but nomen. And that nomen is, if you study calculus, it's a little bit like the derivative. In fact, we might, if we want, we could call this something like discrete calculus. And there is an area of dealing with numbers and functions that gets called discrete calculus, and this would be one example of it. So just a little bit of basics about Figurate numbers. Anybody have any thoughts or observations? Okay. Well, let's move on a little bit. Let's take a look at some more. Here we can make pentagons and hexagons, and this gets a little bit harder. I remember struggling a little bit more to find ways to come up with what these numbers were going to be quickly. Obviously, there's 1 here, and then 5 dots there. Got 5 vertices of a pentagon, and then in the next one we've got 1, 2, 3, 4, 5, 6, 7 more, so we get to 12. And then the next one after that turns out to be 22, and that's takes even more time. But we've got hexagonal, heptagonal. Really, we can go as big as we want in terms of the number of sides. We can go as big as we want, and then we can start building up what these numbers are, and we can look for patterns. So I'm going to fill in some more on this chart. Triangular numbers. We had 1 and then 2, 3, 4 to get to 10, add 5 to get to 15, add 6 to get to 21, add 7 to get to 28, and 8 to get to 36. With square numbers, after 25, we've got 6 by 6, which is 36. We can say we added 11, we add the next odd number 13, get 49, and the next one 15 to get 64. Or we could just say 8 times 8 is 64. With pentagonal numbers, we go to 22, and this becomes a little bit harder. I'm actually going to go back. With the square numbers, let's see. With the square numbers, we had plus 3, plus 5, plus 7, plus 9, 11, 13, and 15. Well, we might wonder if we can do something similar with the pentagonal numbers. And, in fact, we can even start with plus 1 to go from nothing to 1 dot right there to get started. So let's see. Plus 1, plus 4, plus 7, plus 10. Do we have a pattern? It looks like we do. It's not the odd numbers this time, but the differences themselves are going up by 3. So it would appear that the nomen follow a pattern that is arithmetic. They make an arithmetic progression. And that's pretty cool. And we'll explore why this is. I'm going to go ahead and say it does turn out to be the case. This is true. And we're going to explore the reasons why after we compute a few more of these. But we add 13 to get to 35 for the 5th pentagonal number. Then we add 16 to get to 51. We add 19 to get to 70. And then we add 22 to get to 92. I think, hold on, I'm going to go back and make sure that I'm doing that right. 16, 19, 22. Okay. 92. I do not have something like this memorized, so sometimes the numbers begin to look a little funny. But we'll discover some algebra that helps govern these later. And so, going back to the triangular numbers, plus 1, plus 2, plus 3, plus 4. And suddenly, the differences, which have their own patterns within the construction of each figurate number, well, those differences themselves form a pattern. Each one is an arithmetic progression, and it goes 1, 2, 1, 3, 1, 4. And part of it, so long as that holds true, and it does turn out that it holds true, well, the second column gives us the number of sides of each polygon. It has to be, because that's the simplest one after 1 is just one vertex for one vertex, one side. We're counting the number of vertices of the pentagon, hexagon, heptagon. So we're going to assume for the moment that this pattern continues to work, that it's going to be plus 1, then plus 5. So we have an arithmetic progression with common difference 4. So plus 9, plus 13, 17, and so on. And we'll go ahead and compute those. 15 plus 13 is 28, plus 17 is 45, plus 21 is 66, plus 25 is 91, and plus 29 is 120. And we'll do the same with heptagonal numbers, plus 1, plus 6, plus 11, 7, 18, plus 16, plus 21, plus 26, plus 31, plus 36. And then we've got the octagonal numbers filled in for us, and we can check their differences. Add 6, add 6, 13. That turns out to be right. Add 6 to 19. Turns out to be right. Add 6 to 19, we get 25. That is the difference between 65 and 40, sure enough. We always find that pattern. And this must have been interesting and fascinating to early mathematicians. And going back to my theory is that this was being done in Egypt. before Pythagoras, and I think that a certain amount of mathematics, we know that a certain amount of mathematics was imported to Greece from Egypt. We just don't know the lineage and the origins. Maybe Thales of Miletus, who was a Greek philosopher, brought in a certain amount of mathematics. He was a real brilliant guy. He had a lot of cool theories, like the fact that earthquakes. He theorized that our land was actually floating on water, and these days we know that that's like molten magma, and that he thought that that the Earth moved around and there were these waves that caused earthquakes. So real smart guy, even if he wasn't perfectly right about everything. But he brought in some of that mathematics, and I think that the Egyptians were studying stuff like this. They had an intellectual class in running their civilization. Most people in Egypt were slaves. They were farming grain, harvesting grain, building buildings with giant slabs of things, and I'm not a serious Egyptologist. I'm sort of a mediocre studier of history, but I think that they had a class of intellectuals who began creating their mathematics, who were pulled out of the population because they were unable to reproduce. We have evidence that these were people who had um, had abnormal development that kept them from being able to reproduce, and so those people were used as an administrative class within civilization, and they were allowed to then study more mathematics and build more mathematics. And I think that that there's a certain amount of it that just became play, and that they were studying usually what was useful, which was how to count the grain. Um, and their entire number system, sprang forth from how to count the grain. But there were some pieces that certainly seemed playful when you go back and look at it. So there we are, progressions. And now let's take a look at another way to look at this. Now that we've got a filled-in chart here that I prepared beforehand, and we were looking for patterns across before, and now let's look at patterns down. And you know what? You can look for patterns and find them almost everywhere. Diagonal patterns, they exist. You tilt the diagonals to get really extreme bends, and they still exist. But another relatively simple one is just go down. We add 0. We add 0. Obviously, the first column we just have 0. The second column, plus 1, plus 1, plus 1, all the way down. Third column, plus 3, plus 3, plus 3, all the way down. And the next one, this is where we begin to get a grip on what this pattern might be. Plus 6, plus 6. And what do these look like? At least after the plus 0, we get 1, 3, 6, 10, 15, 21, 28, which are themselves triangular numbers. And that's a pretty cool pattern right there. That's a pretty neat pattern. And once you start seeing these cool patterns, you might ask questions, why? And again, the Egyptians were looking at things. They didn't have all the tools that we had. They didn't have the algebra. So, a lot of what they were doing was looking at things picture-wise. And let's take a look at some things that we can see picture-wise. One other type of number that we haven't studied is, I think it gives multiple names. Rectangular numbers, I'm going to call them. I think they may have been called oblong numbers or something else at different points in time. But it's a little bit more than a square. It's this one is 3 by 4, for instance. The simplest one would be 1 by 2. It's where we have one dimension which is one larger than the other. And for us, that's pretty easy to count. We just say 3 times 4, multiplication is fast addition, very fast counting. So 3 times 4 is 12. But you know what we can get here? If we can chop this figure up into 2 identical pieces, And this is part of the reason why we sometimes draw the triangular numbers in different ways. Up here, those don't look quite the same as they do down here, but they do look the same as I presented them on the first page of this document, where we can add a copy of any triangular number to itself to produce a rectangular number. And this helps us compute triangular numbers faster. For instance, if we wanted to know the third triangular number, we could just say, well, 2 of them together makes 3 times 4, and then we can divide that by 2. And we get 6, and we already know that 6 is the third triangular number. And this type of geometric physical observation allows us to go much further. If we wanted to ask a question like, what is the 100th triangular number? And that becomes a pain. That's beyond what I want to spend my afternoon doing. But if we go 100 across and build a row that's 99 across and 98 and so on and so on, and we go up to where there's just 1 up at the top, and we take that whole triangle and we copy it and tack it on the end such that we have the 1 down there, and then 2 more right there, and then 3 more, and they're going to line up. And I did a terrible job drawing a rectangle, didn't I? The point is that 2 of the 100th triangular number, and I'll write it like this for the moment, equals 100 times 101. And so if we divide that by 2, we cut it back in half, we get 100 times 101 divided by 2, which is 5,050 when the dust settles. And I may write, I'll probably usually write that as T100. Triangular numbers just pop up in so many places, both with Figurate numbers and everywhere else when we start doing interesting counting. Yeah, we can compute these relatively easily, and in fact, we can come up with an algebraic formula. And although algebra wasn't available to the earliest mathematicians, eventually they began writing it this way. The nth triangular number is n times n plus 1 divided by 2. And this answers a whole lot of counting problems at the same time. One of those counting problems might be if there are n plus 1 people in a room, how many handshakes are possible? If there are 3 people in a room, or let's say there are 4 people in a room, each of those 4 people can shake the hands of 3 other people. Let's say the first one shakes the hand of 3 other people and then leaves. Then the second one shakes the hand of the 2 remaining guests at the party and leaves. The second to last one shakes the hand of the last remaining guest at the party and leaves. And so that is the third triangular number. And we can get it by saying 3 times 4 divided by 2. So triangular numbers are the answers to a whole lot of counting problems. And we can see physically, we can bring together counting and algebra and geometry long before a lot of that was conceptualized. Okay. So moving on a little bit here. I guess I included a little bit of an exploration of observations we might make about divisibility. And let's see, the 4th Figurate numbers are all even. Let's see, the third ones are all divisible by 3. The 4th ones are all divisible by 2. The 5th ones are all divisible by 5. The 6th ones are all divisible by 3. The 7th ones are all divisible by 7. And the 8th ones are all divisible by 4. And it may not be entirely clear yet what that means, but we do kind of, if we look, we can see 3, 5, 7, and then alternately 2, 3, 4. And it does turn out that the next one would be 9, and then 5 after that, and 11 and 6 after that. Those are the greatest common divisors of all of those, all the numbers in those columns. And we developed some algebra for the triangular numbers already. We'll be able to develop some algebra for all these other figurate numbers a little bit later on. So now constructing layers. I called them layers, being casual. These are the nomen once again. And let's see, here I'm showing the evolution of triangular numbers from one to the next, the plus 2, plus 3, plus 4. And that may be a little bit easier to see with triangular numbers, but we already saw it with the square numbers. We saw the odd numbers being added from 1 to get to the next one. We have 16, we add 9 to get to 25, from the 4th to the 5th square number. And this is going to help us when we get to the more complicated ones. You can see I'm kind of circling a side at a time, right? We have these sides built up, and by circling the sides, that helps us focus in on just the ones that were added in order to count them up. Now let's see what we can do with pentagonal numbers. And our pentagonal numbers go 1, 5, 12, 22. Let's see, plus 7, plus 10, plus 35. And looking at this, what can we do to count these up? Well, to go from the 4th to the 5th, we're adding sides with 5 at a time. And so we're starting with an overly simplistic method. And this is a common theme in mathematics. We're not sure what to do, so we do the simple thing that doesn't exactly work, and then we find a way to correct it. So, going from the 4th to the 5th, which is this line right here, we can see that we add 3 of those sides, where we're adding 5 dots at a time, but then we subtract out 2 because we have overcounted those ones at the corners. And so we correct for overcounting. And with the pentagonal numbers, we're always adding 3 of the 5 sides, right? Like, 2 of the sides we don't have to worry about. That side and that side. They're just going to happen. But we're adding the other 3 of the sides and then the 2 corners between the 3. So what we subtract is 1 less than that 3 multiplier. And so we can see we've got a table of differences right here. These themselves are the pentagonal numbers, and we can see the nomens being added to them. And we can see that they form an arithmetic progression, of course, because we have 1 more 3 added to each one each time. We're always subtracting 2, so it just grows by that column where we're multiplying by 3 for 3 sides, 3 of the 5. Same thing with the hexagonal numbers. These are the hexagonal numbers, and their differences are going to be 4 times. So I'll write it like this: hn minus hn minus 1. We're adding 4 sides with n dots at a time, and we're subtracting 3 corners, because those corners will be where we overcount. So 4n minus 3. And if we look, we plug in n equals 1, 4n minus 3. 4 times 1 minus 3 is 1. 4 times 2 minus 3 is 5. 4 times 3 minus 3 is 9. 4 times 4 minus 3 is 13, and so on. And so we can have an algebraic formula for these nomen, and eventually that's going to help us come up with an algebraic formula for the whole hexagonal number. And so on with heptagonal and octagonal numbers. And for anybody watching this, maybe a good time to try your hand at generating the functional differences with the pentagonal numbers. That functional difference was 3n minus 2. And with hexagonal numbers, it was 4n minus 3. And then, just as a hint, with heptagonal numbers, it's 5n minus 4, 5 of the 7 sides minus 4 of the 7 corners. 36 is 5 times 8 minus 4. So now, making use of patterns. I'm going to leave this as an exercise for anybody who wants to fill this out. You know that you've learned something well when you can relatively quickly apply the patterns that you've learned, and this is a chance for anybody to go through and fill out the rest of this chart. And again, I'm going to save this file and keep it on the page for subscribers to the Math Club, which we have not yet generated, but we will create that page in the next couple of days. And now we can fill that out. I won't dwell too much on that page where we've got that, but we've gotten this far. I'm going to go a little farther. We talked about building formulas, and with triangular numbers, so triangular numbers, we know that the nth triangular number is n times n plus 1 divided by 2. Then the formula for the square numbers, that's even easier. It's just n squared. That one is arranged most easily for us to count. But then we have pentagonal numbers. And what is that going to be? Well, we can use those nomen that we were studying earlier. Let's say that we want to know the 8th pentagonal number. Well, we could start with 0 dots. That's the 0th pentagonal number. And we can add all of the nomen, all the changes. 0 to 1, that gives us the 1st pentagonal number. And then we added 4 to get the 2nd pentagonal number. And we added 7 to get the 3rd pentagonal number. And what we're adding, we determined that we have a formula for that, which is 3n minus 2. And we're going to go up to the 8th nomen, 3 times 8 minus 2, which is 22. And now what do we do to turn that into something algebraic? Well, what we know is that this is an arithmetic series. And just in a similar way to the way that we, with triangular numbers, we put the dots together in a way that made them fit. Well, I'm going to kind of fast forward in mathematics historically and do something that we think of Gauss as doing. We have a story about him, apocryphal or not, where he understood that when you had an arithmetic series, you could turn it around backward and write that same series again. Wait a minute. Perhaps I should leave out the 0.
Mm.
And what happens here is that when we look down each column, we get the same sum. And when we think about it, of course we do. These change by 3 in both directions. That was what we learned about the differences, is they're constantly changing by 3 at a time. So now we can say, hey, 2 times the 8th pentagonal number is going to be, well, how many numbers in each of these lists? Oh, well, 8, because we added 8 nomen to the 0th pentagonal number. 8 times, well, whatever the sum is down each column, which is 23. And then divide that by 2, and let's just check. I like checking myself. Oh, there it is right there, 92. The 8th pentagonal number. And, well, let's see what we can do algebraically then. While that first number, 8, that's just our index right there. And then that 23, where does that come from? Well, it's 1 plus 3 times 8 minus 2. So most generally, we can say 2 times the nth pentagonal number is going to be n, and then times the nomen plus 1. The nomen, 22, the 8th nomen, the nth nomen plus 1, because every column will have to have that same sum. So now we have the nth pentagonal number equal to n times, adding what's in the big parentheses, 3n minus 1, and all of that divided by 2. So we do have a formula. And once again, the square number formula makes it seem like everything's going to be easy. But we look at the other form, the triangular number, the pentagonal number, and it looks like it's hard to see, what's going to happen there. What's the complication? But it's not actually that bad once we realize that the nomen, if we wanted to know, let's see, how do we want to represent figurate number in general? Let's say I'm going to make n sub k n. I'm going to let that be the nth k-agonal number. And let's see what we can do here. Well, studying this and thinking about what the nomen is going to be. The nomen, let's see, for the pentagonal number, it was 3 times n minus 2. It's going to have 2, that 3, it's 2 fewer than 5 sides. So if we have k sides, we should have k minus 2 sides with n dots on each side. And then we want to subtract k minus 3 vertices. Just to make that clear, let's go back to one of these pictures. With pentagonal numbers, we added 3 sides and we subtracted 2 vertices. Did I have a picture of it? Did I not on this document? But we can imagine doing this for larger and larger figures. K minus 2, and the number of sides that we actually have to add onto number of vertices between those sides. So count simply, correct for overcounting. Count simply, correct for, okay. So we have the nomen. And now we follow the construction that we did up here. And we say 2 times the nth of these k-agonal figurate numbers is equal to n times the nomen plus 1. I'm going to go ahead and multiply out this nomen. K minus 2 times n is, we're going to have a kn term, then minus 2n minus k plus 3, but it's going to be plus 3, but then plus 1. So plus 4. And then we are going to divide by 2. And it's different ways that we could write this. I hope I've done this right. If anybody can check my work, let me know if you see any mistakes there. Kn minus 2n and then minus k plus 3 and then plus 1. Okay, I think that's right. Like we have a formula. I'll go ahead and rewrite that. This is the, we said it verbally, be the nth k-agonal number. And I see people leave that term in quasi-factored form at times. So you may see this written differently elsewhere. But I just want to check and see whenever I see something quite this ugly. I'm going to plug in k equals 5 and n equals 8. See if we get that same 92 that we did for the 8th pentagonal number. Plug that in and we get 8 times 40 minus 16 minus 5 plus 4, all divided by 2. That's 8 times 23 divided by 2. We do. That was the same 92 that we've seen several times earlier. And that's pretty nice. All right, I'm going to go ahead and call this a good stopping point. It's a really nice stopping point. I didn't know how far we would get or how much of the history that we would talk about. Again, I'm not the greatest mathematical historian, so if you're interested, I'm sure that you can find some good things on the web, and perhaps eventually we'll take what we're doing here at the Math Club and compile it and put everything within a little bit of historical context with some good math lessons along the way. Thank you for joining us for the first episode of the Math Club.
Thank you.
Thank you.
Thank you.
Is there time for a quick question?
Oh, absolutely, absolutely. Basically, I'm probably just gonna cut recording there. Or maybe I won't. Maybe I'll cut this out. maybe I'll include your questions. I kind of, I thought of myself as being sort of open in the middle to quite. In the future, feel free to stop me at any point in time. Really, this is casual. This is for all of us. Me included, to be as educational as possible. I assume a lot of times I'm going to see things I didn't. In fact, this is actually the best I've ever described this. I usually have never sat down and talked through figurate numbers quite like this before. So this idea of taking the nomen and adding 1 as that term, like suddenly that's simpler to me than it's ever been before. So feel free anytime we're doing this to just barge on in and ask questions. I've got the chat window up too, so I can see, when anybody may have a question there. But yeah, go ahead.
Sure. Thank you. Yeah, it was interesting because when you were going through the preliminary setup of it, I started thinking about when you were looking at it n-2 as the number of sides being added at every successive step when going to the next inagonal number. I was reminded of the formula for the number of degrees in a polygon, where you do the number of sides -2 times pi.
Right.
And it seemed like it was a similar relationship, but I was trying to work through that. And then Charlie over here is like, hey, Dad, if I take the difference between two rows, I get triangular numbers, right? It's like, yes, you do. Very interesting.
Oh, your son saw the differences as the triangular numbers. That's fantastic.
He jumped
I love that.
by 5 minutes. Yeah. Oh,
I love that.
Very
Oh,
proud.
and you know what? And okay, that's wonderful. So our 9-year-old viewer has discovered something that's pretty cool about that. And I'm trying to remember. I know that we can do this physically and see where that triangular number pops in. And I want to see if I've kind of drawn all over this. Maybe I'll use the fourth pentagonal number here and see if we can carve out, let's see, the fourth square number is 60. So we want to carve something out that would be that triangular number. So we carve out those 6 and we should have the fourth square
16.
number. And you can see if we kind of rearrange the dots just a little bit, we have like 4 by 4 in the rows.
Mm-hmm.
Now let's do it again. Now let's try to go from the same sort of vertex, like carve out those right there. And we take those out, and suddenly what remains is the fourth triangular number.
Oh, wow. And that's basically that's the proof behind that basic geometric theory. Is you decompose the n-gon into triangles.
It's physically it's the same thing. Physically,
right.
It's the same. Right. Exactly. Yeah. Absolutely. And it gives us actually another way if we wanted to come up with any one of these formulas like this, right?
Yeah,
I'm going to do that real quick
on my notepad. But yeah, it was a lot of the Gaussian derivation of it.
So that was the fourth pentagonal number was equal to the fourth triangular number plus the third triangular number plus the third triangular number. And so the nth pentagonal number should be equal to the nth triangular number plus the n minus first plus the n minus first. In general, we should be able to always carve out those triangles that way. And then that would be equal to n times n plus 1 over 2, and then n minus 1 times n over 2, n minus 1 times n over 2. And let's see, that's going to be 3n squared minus n over 2, and we could rewrite that as n times 3n minus 1 over 2, which was, in fact, our formula for the nth pentagonal number. So great, we've derived that another way. And you know what, I've done that once before. Yeah, a long time ago, probably 12 years ago or so, when I was writing problems for a math contest. That somebody we went to high school with actually was administering, but I was writing a problem, and I came across this. I noticed it, but I hadn't done this in so long that I didn't think of this as the way that I was going to go this time. I kind of wanted to use the nomen because that those patterns jump out. They're nice to explore, right? But this is another way to do it. If we wanted the nth hexagonal number, it would be the nth triangular number plus
4 copies?
n minus 3. Oh, yeah, in this case, sorry, I was going to do k minus 3. But, no, wait.
Oh, that'd be 3.
3 copies of the n minus first triangular number. And, yeah, we can derive all these formulas that way as well. And if we do that, we should get that same formula that we came up with before. Pretty neat. Yeah, thank Charlie for me.
Will do. Like, don't forget to tell him, Dad.
That's fantastic. I love it.
Hopefully I'll be able to rope him in next Thursday night too. It's going to take some negotiation on bedtime with my wife.
Understood. All right. Well, he's welcome to join us. Anyone else have any thoughts before we call it an evening?
I have one quick question.
Yeah.
So I vaguely remember many, many years ago sort of learning that the Greeks thought of, rectangles as sort of sacred. And that's one of the reasons why in their temples they have all of these rectangular windows and things like that. But I'm just kind of curious, I'm seeing these sort of repeating and expanding patterns and just wondering, is this something that people used historically to make buildings? It just seems like the sort of thing where if you're expanding on structures or something like that, it's an easy way to calculate the size of things that you need.
So that's a good question. And again, this is one where my historical knowledge is lacking. But I will say this. I know that, for instance, the Egyptians, while they developed their own number system where they could use to, count, but they didn't even have like the multiplication operation. Their method for multiplication was this strange method of like taking things and doubling them, and then, just counting up what was there when they were done. Repeated doubling, sort of a binary system, but it involved like a very physical representation of it in order to just double and double and then count what was there. There's part of me that wonders, so much of what they were doing when they counted was it was the process of arranging land and plots of land and knowing how much grain was going to be harvested. To be able to know all these numbers ahead of time meant that they were planning civilization in a very solidified way. In fact, even when you get to the fourth power of 10 within the hieroglyphics, there are two ways that's represented. One is with a bird, one is with a frog, and that's because the Nile, when the Nile was abundant, you would have these animals, the frogs in particular are amphibians, right? And so if things are drying up, you don't have an abundance of frogs. So, in order to represent 10,000, which was, a number that you would rarely go up to, except if you're an administrator, they just use things that represented abundance. So I wonder the degree to which, a lot of their mathematics was, is based on figuring out things with lands. And now when you're working, a lot of things can be done with squares, right? Of course, like a river like the Nile bends and twists, and every now and then they may have done something like use pentagonal numbers to estimate the area.
Interesting,
they didn't
yeah.
have, without this concept of multiplication, they didn't have this concept of area as well, right? So I speculate that they were using counting as a substitute for thinking in terms of area. So they may have sometimes used these other Figurate numbers that are more complex than square numbers. But let's face it, when you are building and you're trying to pack people into spaces, most things you do with rectangles, because those right angles, they just fit together at the corners, right? So just the logistics of that led to but if you had containers, if you have like a container of grain, a silo, any kind of grain storage house, that might have been set aside from the buildings that needed to fit together, they often use circles. And the reason for circles is because it's what's called the Isoperimetric Problem, which is if you are going to capture the greatest amount of area with the smallest amount of fence or walling, then the answer to that optimization problem turns out to be a circle. So we do know that they were coming up with a way to formulate the area of a circle given its radius, and they were measuring things in cubits, in distance from the tip of somebody's finger to their elbow. They can have the slaves out there measuring things, and somehow I don't know how people's fingers to elbows were so uniform, but somehow they were able to make these amazing pyramids by having things so precise that way. So they found ways to make it work. And it really is, it's a spectacular example of using the tools that are available to you, and you become more ingenious over time according to yeah, your needs and your tools. So that's what they did.
Thank you.
Sure. Did I answer your question? I started rambling out. What was the original question?
So I was asking about like building structures. So yeah, actually the land use and like the estimation of say like farmable
All right,
or
yeah.
arable land, that's actually pretty interesting. And I can certainly see somebody doing this. It's a nice physical representation that you can just like literally just have somebody count dots.
Right on.
Yeah.
Well, oh yeah, but there's so few people. I don't know if anybody wants to introduce themselves. I'm sure that we'll have different people from evening to evening at times, and I'm going to start advertising this a little more broadly to get it to grow. I have not done any kind of Facebook promotions yet because I wanted to try this out once and just see how it felt. But Rob is somebody I've done business with and known for 17 years or so. John and his son Charlie. John is somebody I was on math team with in middle and high school. He was another of the Olympiad participants from my high school. And John is somebody I met at a bar in Birmingham. Is that John? Do we have a acquaintance before that?
That's the first I remember. So.
And we've talked a little bit of cryptocurrency since. And Amanda's my wife. sorry, and she didn't put her name up there. Maybe throw something up there in the future, or I guess you can disguise yourself if you want.
It's just the name I set up with Zoom.
Yeah. All right, and by the way, feel free. Especially while the group is small, I have no idea what I'm going to do next week. I didn't know. I really didn't know how long it would take to talk through this, but this feels like sort of a relatively complete, lesson in Figurate numbers. So I'll choose something completely different for next week. But if there's ever anything that you have curiosity about, feel free to suggest it. And I may get to it at some point. It may depend on how much material I already have prepared or how much, I may want to do a little bit of reading. I'm enjoying learning a little bit more of the history of mathematics as I go. The longer I've been teaching some things, because it's really awesome to see what it was that people did, and even just to speculate. Like I said, a lot of my in-game thoughts here are speculations, right? So I really enjoy the process of going back through the history for any topic I prepare and thinking through my own speculations, because I feel like that's actually a better way to be learning math anyway. To blind yourself from the modern exposition and the formalism, and just think, what would we do?
Sounds
All right.
good.
All right, everybody. Thanks for coming.
All right. Thank you.
Have a good night.
Have a good night.
Good night.
Thank you. Good night.